Hello everyone. In this video we are going to talk about numerical differentiation and integration in Python. And for that we need the Scipy, and we need to bring in the integrate from Scipy for integration, and then from Scipy miscellaneous we need to import derivative for numerical differentiation. So let's go ahead and do it. So here I define a function x cubed, and then I say the derivative of x cubed at x0 equal 1 is, and I use the derivative method. I pass to it the function, I pass to it the test point, and I pass to it the step size, which is 1 to the negative 3. And I ask it to give me the value of the derivative, right? And if I go ahead and run this for you, you see the value it gives me is this much. So clearly this is not done using exact derivative. This is a numerical derivative which can be done using basically the forward, backward, or the central difference method. And you can see that number here, right, which is basically f at x plus dx minus f at x divided by dx, right? This is the forward method. Then you can use the backward, you can use the central method. Anyways, this is your dx, this is your x naught. So one time you pass 1 to it, one time you pass 1 plus this number, you calculate the two f's, subtract, and then divide by this dx, and that could be an approximation that you will see here. And you know the exact value is 3, right? Because derivative of x cubed is 3x squared, and at 1 it's going to be exactly 3. So this is a very good approximation of 3, as you can see here. The smaller you choose this number, the more accurate you are going to take that derivative. The second method is, and here is if you want it at more than 1 point, you want a vector of derivatives. So here you create a vector x. Here let's say you want to find all the derivatives between 0 to 3. So between 0 to 3, you're going to choose some step size. Again, the smaller the step size, the better the approximations are going to be. But let's say here you're going to make 31 points between 0 to 3 at the step size 0.1. You calculate, you pass this vector to the function f. You get the vector y, and then use the gradient method, which is basically the difference between the consecutive elements. In MATLAB, this command is called diff. It gives you the value of current y minus previous y, and then that previous y minus the y behind that, and so on and so forth. The same thing for x. So here you get the gradient, or the difference in y and x, consecutive ones, and then you divide that dy by dx element by element, and that is an approximation, forward approximation or backward approximation of the derivative, which is in more than 1 point. It is going to be evaluated at all the points from 0 to 3. Okay, so this is derivative at more than 1 point. This is derivative at 1 point, and you can see here this is your vector dy, and this is your vector dx. This is your dx, this is your dy, and this is the element by element division. So you divide this by this, you divide the second number by the second one, and keep going. You see the dx's are all constant. Why? Because my step size is constant. The dy's are not, of course. The function is not linear. And these are the derivatives. So this is the derivative at 0, right? Which is almost 0, as you can see. And then we have the other derivatives calculated at other points, right? So this is at 0.1, this is at 0.2, 0.3, 0.4, 0.5, 0.6. Let's see if there is more, or that's it. No. 0.7, 0.8, 0.9, and 1. And you see the derivative at 1 is 3.01. Should be 3 if you remember. And you see this one is not as accurate as this one. Why? Because here I'm using a step size of 0.1, and here I use the step size of 100 times smaller. So of course this is going to be more accurate. But anyways, you clearly can see that the gradient method or this derivative method both work. Then we have the integrations, and here we have to We can define any function. Let's say this time we want to integrate the function s(x)² plus 5, a single variable function, and we want to integrate it between a lower limit of 1 and upper limit of 2. So the method we're going to use is scipy.integrate.quad. So it's the quad method, which is Simpson integration, and you pass to it the function, and you pass to it what? The upper and the lower and the upper limits, and it is going to give you 2 numbers instead of 1. If you look here, when it is printed I, it gave me 2 numbers. One is the actual integral, and the other one is this guy, which is the possible error in the integral, okay? But the number that you should care really is the first one. This is the potential error in the integral, okay? So you can see that the integral is correct, right? Because x² is 3 over 2 1 over 3, I'm sorry, 1 over 3 x cubed plus 5x. And if you plug in 2, you're going to get 8 over 3 plus 10. If you plug in 1, you're going to get basically 1 over 3 plus 5. And if you subtract, the number should be 7 and 1/3, right? Which you can see over here. And the next one is a double integral. If you want to do double integral, here I show you 2 different versions of double integral, because sometimes the domain over which you integrate has only numbers for x and y. Sometimes there are functions. So sometimes you have something like this. This is your function to integrate xy cubed, and then the limits for x and y are just pure numbers. In this case, the integral is very easy. So here you pass the first 2 numbers and then the second 2 numbers for x and y, and that is gonna be, that's all you need. By the way, since it's double integral, the method instead of qual is called double quad, DBL quad. So you pass to it the function, and here you see that for me, to make the life simpler, instead of using the function, using the def method to define the function, I used an anonymous function or inline function. That's another area that the inline functions are useful when you want to pass them to another function or another method. So here I define my function as xy cubed. Using lambda functions, I pass it to it. These are the limits for x, these are the limits for y, and that is going to give me I1, which in this case, you see the number is 0, and this is again the error, the possible error in it. And the second time, I want to calculate the integral of xy, but this time the limits are x are numbers, but the limits of y are between 2 lines. So these are functions instead of numbers for y. Since they are functions, I have to define functions as my limits, and that's what you see I'm doing here. So these are the limits on x, 0 and 1, but for the lower limit, it's x. So I say, hey, my lower limit is what? You see, for my lower limit, I use an anonymous function. Say my lower limit is x, but what is x? It's an anonymous function of x. Then my upper limit is 2 minus x, where again x is the input and it's an anonymous function. So you see, not only I can use anonymous functions as the main area, the main function under the integral, the integrand, I can also use them for what? Use them for upper and lower limits if they are functions like this and they are not pure numbers. And here is my number here, and this is again the potential what? Error. So the method is called quad, whether single, just quad, or double quad. And for derivatives, I can use the division of the gradients, or I can use this derivative method here. So this is numerical differentiation and integration using Scipy, and hopefully this video is useful to you. I'll see you in the next lecture. Thank you.